This video will present the findings from the paper entitled Variational-Based Optimal Control of Underactuated Balancing for Dynamic Quadrupeds. The paper proposes a novel quadratic programming-based control strategy that enables the MIT Mini Cheetah to sustain balance on two legs, even in the presence of mild push disturbances. The two primary components of the proposed control framework are first, a linear controller that solves an unconstrained optimal control problem, and second, a quadratic program that uses the output of the linear controller to approximate the optimal input-constrained solution. The controller, referred to hereafter as the VBL-QP controller, employs a control strategy aimed at minimizing the cost to go of the system, according to the following cost function. In this cost function, the variable s quantifies the deviation of the robot's current state from its desired reference state, and delta u is the variation to the nominal control input u. The optimal cost to go of this infinite horizon system is found by solving the algebraic Riccati equation. Using a control strategy that minimizes the cost to go, the controller is able to maintain balance by simultaneously driving the state error to zero while avoiding control inputs that threaten to cause the robot to lose its balance. Two complications of quadruped balancing pose obstacles to direct implementation of this control strategy. First, this optimal control problem requires linearized aerodynamics, and second, the optimal control problem does not allow for constraints on the variation to the control input. Even using a simplified model of the robot, its dynamics can still contain elements of the special orthogonal group SO3. Traditional linearization techniques do not translate to this type of nonlinear manifold. To account for this shortcoming, we implement a linearization technique referred to as variational-based linearization. Variational-based linearization, which involves linearization about a reference trajectory, exploits specific variation expressions on the nonlinear manifold SO3, which allows for parameterization of the error directly based on infinitesimal rotations. The ability to parameterize the error in this way offers a significant advantage over typical dynamic models that employ Euler angles, which can suffer from singularities, or quaternions, which are significantly more complex to deal with and suffer from issues like the unwinding phenomenon. Recall that control input constraints are not included in the previously mentioned linear optimal controller. Including constraints in that formulation necessitates computationally intractable solution methods, such as the Hamilton-Jacobi-Bellman partial differential equation. To avoid such solution methods, our controller replicates the HJB minimization, but does so using the unconstrained cost to go, which comes from the linear controller, as a proxy for the constrained cost to go. Since the cost function is quadratic, and the friction cone constraints are approximated as linear friction pyramid constraints, this optimization is a quadratic program. The replication of the minimization step is useful because it enables the controller to reason about future consequences of present actions via the cost to go. Despite the challenges of underactuation and a reduced support polygon, the controller is able to balance the robot on two legs, even in the presence of push disturbances applied in various directions. Empirically, we find that the additional information afforded by using the unconstrained cost to go enables underactuated balancing in extreme low friction regimes, suggesting that underactuation, not friction, can be attributed as the main challenge for balance on two legs. In this clip, the robot is responding to a series of desired orientation changes commanded using an RC controller. The limited set of wrenches that can be generated by the reduced number of stance legs makes even simple orientation changes challenging for conventional QP balance controllers. The VBL-QP controller, however, is able to reason about the robot's dynamics and exploit angular momentum to enable orientation changes.